All right, let's come back, and we will have an extension part on the expansion of the universe. Again, I emphasize that this will not be tested in the final exam. Now, gravity is actually an interesting phenomenon. Newton, in some 300 years ago, Newton discovered the universal law of gravitation. But at the beginning of the 20th century, Albert Einstein actually formulated another theory of the law of gravity. Okay, and in Einstein's idea, gravity is an effect of space-time. He postulated that matter, the existence of matter or energy, it causes space-time to curve. Now, this is a picture. It's not a real thing, but it's a picture. Give you an idea of how Einstein can thought of gravity as being a space-time curvature. Imagine now you have a massive object, and the massive object deforms the space-time around it. So the space-time is like a fry big, and because of the presence of this massive object, the space-time is curved. Okay, so you have a curved space-time here. And suppose now I have another object moving close to it. Because the space-time around this object is curved, so the object that is moving, it can never move in a straight line, but it can move just around the space-time. It curves the space-time, and the resulting motion will become a curved motion. That's why the object gets diffracted when it is getting close to the massive object. Newton says that this is a law of universal gravitation that attracts the object together, but Einstein says this is a space-time curvature. Now, this is Einstein field equation. Einstein field equation described in the presence of energy and matter, there will be a curvature in space-time. Now, this quantity, T mu nu, is called the energy momentum tensor. It is related to matter and energy. So what actually Einstein postulated that whenever anything that has energy or momentum, okay, including light also have energy and momentum, right? Anything that carries energy and momentum will involve in gravitational interaction, and it will produce a curvature in space-time. Okay, so not only matter will produce a curvature in space-time, but all the stuff that have energy and momentum will cause the space-time to curve. And the term that describes the curvature of space-time is called the Einstein tensor. The Einstein tensor is very complicated, but it involves something that can describe the curvature of space-time. And there's a term called cosmological constant. Now, this is not present in a traditional Einstein equation, but later people find that they have to add this term. Actually, the Einstein equation permitted the presence of this term called cosmological constant term. And the cosmology, this system typically matter and energy that causes curvature of space-time, but allowing this term, which is called the cosmological constant, actually that's the presence of this term can cause a space-time to curve. But this term is not related to matter. It's independent of matter. Now, Einstein, he first set lambda to be larger than 0 in order to produce a repulsive force in space-time that balance the gravity force. Okay, and by doing so, he arrived at a static universe, a universe that does not expand or contract. He used this cosmological term, which origin is unknown, to produce a repulsive force. And that repulsive force just balance the gravitational force of matter. Okay, so these two forces balance, so he arrived at the universe that is stationary. Okay, now, but Einstein later abandoned this term Why? Because later he found that Hubble has observation data which shows that the universe is undergoing expansion. The universe is expanding steadily. Okay, so he abandoned this term later. But in the last century, at the end of last century, and also in this century, people find that lambda is not actually it's actually present, because they discovered that the universe is now undergoing accelerating expansion. Now, if you ignore the cosmological constant, then the expansion of the universe will decelerate because of the gravitational force between matter. That includes also the dark matter, which cannot be seen. There are a lot of dark matter, and the dark matter actually produces a gravity force that tends to slow down the expansion of the universe. So the Big Bang starts at about 13.7 billion years ago. That's the start of the Big Bang. That starts the universe. And after the Big Bang, you imagine that the cake is a universe. So after the Big Bang, the universe expands. But due to the gravitational force between the matter in the universe, it curves the space-time. So eventually, the expansion rate will slow down. Okay, so the expansion rate decelerate. Okay, but people don't know why. During the past 7 billion years, the universe expansion rates start to accelerate. So now the universe is expanding faster and faster. Okay, it's just an accelerating car, just like accelerating car. It's moving faster and faster now. So the expansion, the universe is getting bigger and bigger, and in an accelerated way. Okay, the expansion is accelerating. Okay. Now people don't know why the universe is undergoing an accelerated expansion. So they postulate that the cosmological constant term gamma is not zero. And that term, due to nothing at all, cause an repulsive force in space-time that expand the universe in an accelerated way. Okay, so that is a miracle. The cosmological term has to be there. And the cosmological term constant, if larger than zero, will give rise to a repulsive force that accelerate the expansion of the universe. Okay. Now this sounds quite absurd. In the vacuum, we don't have any matter, right? But we still have this cosmological term that produces a force of gravity that is repulsive. Okay. Now Einstein, with this cosmological term, Einstein actually postulates that gravity have a repulsive component. That repulsive component is characterized by this cosmological constant. When gamma larger than zero, that is equivalent to a repulsive force that comes from vacuum, that comes from nothing. It is a characteristic of space-time itself. It is a characteristic of gravity itself. It does not come from matter. Okay. Now this is rather absurd, but we have to believe it, because that is what people observe. The universe is now expanding in an accelerated manner. Okay. Now we can have a heuristic simplified Newtonian derivation that give rise to the correct equation described by Einstein equation. Now this derivation is actually not correct, because we based on Newtonian mechanics. But the dependence almost gives us a correct answer. Okay, just a kind of dimensional analysis actually. It just gives us a correct answer for the accelerated expansion. Now you consider a uniform sphere of mass m. Okay, that's full of matter. And as a distance r, which is the radius of the sphere, you have a small mass m here. Okay. And if you consider the attraction force between this large mass, which is the mass of the universe, and the small mass on the surface of the universe, then you have this term due to Newtonian gravity. So the force is gmm over r squared with a minus sign. and the force is obviously attractive. Okay, so that is a force that slows down the expansion of the universe because the force is attractive. But we also have a repulsive force. The repulsive force is due to a constant density from the vacuum. This is absurd. If that is a vacuum, how come you have a density? But let's assume it being true at this moment. In the vacuum, there is a certain kind of density. I call it rho prime. That density remain constant during the expansion of the universe. Okay, so rho prime remains a constant no matter how the universe expands. That is a property of space-time. So with that density, the stuff inside this large sphere will be equal to 4/3 pi r cubed, which is the volume of the sphere, multiplied by that density. And that is the equivalent mass of that stuff. And it produces a gravity force. So if multiplied by the small mass m, the two mass multiplying together, and we have another constant g prime that characterizes the repulsive nature, and the gravity force is also proportional, inversely proportional 1/r². So we have this multiplied by g prime divided by r² as a repulsive force. The force is repulsive, so there's a plus sign instead of a minus sign. Now, rho prime is independent of matter. It's not a kind of matter. It does not decrease as the universe expands. Now, if it's a matter, then as the universe expands, the density will get smaller, right? If you have ordinary matter, if the universe expands to a larger volume, the same matter is there, so the density must decrease. But this is a property with the vacuum. So as the universe expands, the density of this stuff will not decrease. Okay, so this is called vacuum repulsion or dark energy. The energy associated with this stuff of repulsion is called dark energy. Okay. Now let us go through the direction. Now you have the dependence of the gravity force as 1/r². But for the vacuum stuff, for the vacuum force, you have the dependent r³ here in numerator, and the denominator dependence is r². So one of the r will cancel, right? Two of the r will cancel, leaving you an r in the numerator. So the vacuum repulsive force is proportional to r. Now, so let's us simplify the equation a bit by writing the other two constants to replace this g and m. The g and m are not important. We can always write the acceleration in terms of two other constants, which replace this g and m. Okay, and also g prime. Now I use a capital omega m to denote the effect of the attraction force of matter. So that becomes omega m over 2r² with a minus sign. Now the 2 here is only a convention, okay? And we use a omega lambda to denote the repulsive force of the vacuum repulsion, okay? Now you see the dependence here. The gravity force is inversely proportional to r², and the vacuum force is proportional to r. So what happens when the universe is getting large? When the universe is small, just after the Big Bang, r is small, right? When r is small, the gravity force dominates because 1/r² is large, right? So the gravity force dominates over the vacuum repulsion. So the gravity force pulls the universe together, the matter of the universe together, and slow down the expansion. So that's why we observe the first part. So the acceleration slowed down at the beginning. But how about in the past 7 billion years? When the universe is getting large, r is large. So when r is large, 1/r² becomes small, right? And the vacuum term, which is proportional to r, will increase. So the vacuum repulsion will dominate over the gravity force, and that results in the acceleration. The acceleration now becomes positive. So the universe is getting in an accelerated expansion, expanding faster and faster. Okay, so that's explain why the universe is now undergoing an accelerated expansion. Okay. Now, omega m actually depends on the amount of normal matter and dark matter in the universe, but the cosmological constant lambda, which is proportional to this omega, is dominant when the universe is large. And people, they are actually sending a satellite to space to measure the cosmic microwave background radiation. Okay, there's a small irregularity in the cosmic microwave background radiation. That is the echo of the Big Bang. When the universe is small, the universe is very hot and filled with radiation. Now we can also measure those radiation. But due to the expansion of the universe, the wavelength of the radiation is redshift, and so that the radiation has now become microwave. So by measuring this microwave, we know by measuring this irregularity in the microwave, we can know how much normal and dark matter in the universe and how much the vacuum repulsive stuff is in the universe. So our current understanding is that omega m is about 0.3 and omega lambda is about 0.7. So in your project, you are required to use this number, substitute into this equation with this acceleration to calculate how fast the universe is expanding now. And you can extrapolate forward in time and backward in time to see the future of the universe and the past history of the universe. And by tracking the past history of the universe, you will be able to deduce when the universe began. And that is the Big Bang. Okay, so you actually can estimate the age of the universe based on this model. So this is one of your project. Okay, so you probably haven't imagined that you can use a simple numerical equation to calculate the expansion of the universe and know the age of the universe, but you can now do it. Okay, so that is the idea. Now, this is our understanding of the stuff that make up the universe. Normal matter, including interstellar gas, and also the stars and the planets, including us, they make up about 4% of the total stuff in the universe. And about 23% of the stuff is dark matter. Dark matter cannot be seen. It only produces gravitational interaction, but it does not produce any other interaction. So when you have a dark matter colliding with a normal matter, the only force between them is gravity. So the dark matter actually bypass the normal matter without exerting any pressure on it. Okay. Somebody has a question? No. The vacuum density is actually not related to the temperature of the universe. Okay. And we also, the most dominant part is the dark energy, which is the vacuum force that we mentioned. It constitutes about 73% of the stuff in the universe. Okay. So our universe is so dark. 96% of the stuff we cannot see. We only can see 4% of the stuff, including ourselves. So it's quite irony. And other questions? Yeah, there are dark matter around you, but the density is so low. The density of dark matter is so low that you couldn't have noticed that. The dark matter is actually distributed in a very wide range, in a very large scale. If you see the dark matter in the scale of the galaxy, you will find a lot of dark matter. It actually dominates over the ordinary matter. It actually extends much further away from the galaxy itself. For the Milky Way galaxy, the Milky Way galaxy is about 100,000 light year across. But the dark matter halo, you imagine a dark matter halo extending several hundred, about 600 1,000 light years in a halo around the galaxy. So the dark matter is actually distributing in a much wider range than the normal matter. And so the density of the dark matter could be very low. And yet they dominate over the normal matter when the large scale matter contract under gravity, it dominates over the normal matter. Okay. Does our universe have a boundary? I don't know. What we have now is an observable universe, and according to our understanding, the universe geometry, the space-time of the universe is flat. It's almost flat. So theoretically, we don't have a boundary, but we don't know. Okay. What we can observe is a so-called observable universe, and we have a horizon beyond which the expansion of the universe will be faster than the speed of light, and we cannot obtain that signal. So beyond the horizon, matter that is beyond the horizon, when they emit a signal, electromagnetic signal, we could never receive that. So we can never see the object that are beyond the horizon. Okay. So we only can observe a certain range of the universe. So we don't know actually the universe is finite or not. Okay. Now, this part I prefer not to teach you. This is about finding the gravitational potential of a sphere by using a direct integration. Now, I let you try to understand it yourself. We actually divide the shell into a lot of thin rings, and we calculate the gravitational potential between the ring and a point along the z-axis that go directly to the center of the shell. Okay, and that requires a typical integration. And after doing that, after doing all this part, we find this result. And outside the shell and inside the shell, we obtain two different results. And inside the shell, we find that the gravitational potential is constant. And outside the shell, we find the gravitational potential is just like that of a point mass. Now, that is a rigorous proof using integral calculus that the shell theorem holds. Okay, the potential inside the shell is constant. The potential outside the shell is just like that of a point mass located at the center. Okay, so I better not bother you with the proof, because that is boring, and that requires some mathematical skills that might go beyond your understanding. So I leave it to your study. And if you don't understand and you want to discuss with me, then please come. We may arrange a meeting in Zoom to discuss about that. So we better stop here for this chapter, and we can proceed to the chapter with fluids. That is chapter 9. Now our course is called Mechanics, Fluids and Waves, right? Introduction to Mechanics, Fluids and Waves. But we only have one chapter in fluids, and that's chapter 9. So we would like to have a brief introduction on fluids. We will not go into the details. We will not even mention about the viscosity or air resistance. We will not mention that. We will only discuss about ideal fluid motion. Okay, so that's a simplified discussion on fluid. Fluid dynamics is actually very difficult. So for introductory course, we better simplify all those things and have the very basic introduction of it. First, we discuss about density and pressure. I think you know, all of you know about density, right? Density is the mass per unit volume. So if I have a small volume here and I measure the mass of matter in this small volume, I call delta M. I divide delta M by the volume of this volume. So I have delta M divided by delta V. I got the density rho. Now you may wonder why I use this notation, why I use delta M and delta V instead of just the total mass divided by the total volume. Now, because the density could be non-uniform inside an object. Now, for water, I think water is almost incompressible. So you would have the density of water almost constant throughout the whole object. So the density of water is almost uniform. But for air, for example, you will see the density of air to be much higher at the sea level than at the top of a mountain. If you are at an altitude of about several 1,000 kilometers high, just like when you are at the top of a mountain, then you will see that density of air is much lower. So the density might be a function in position. If you go to a different position in the atmosphere, you have a different air density. So that's why we cannot assign a unit density to the whole atmosphere. And to measure the density in different parts of a fluid, we can assign this notation. We can use a small volume, a microscopically small volume. But still, the volume is large enough so that it holds a lot of molecule. Okay. Suppose you have a large beaker of water, and I want to know a density here at this position. So I use a small volume, which encloses a lot of molecules, and I measure the mass here divided by the volume of this volume, and I get the density here. If I do it in another position, I may get a different value. So that allows me to measure the density at different position. And the unit of density of course is of kg per meter cube. And if the fluids or the matter is incompressible, the density is the same everywhere, we can simply replace delta M over delta V with M over V, where M is the total mass and V is the total volume of that matter. Now, incompressible fluid, as I say, if the matter is not compressible or very difficult to compress it, then the density will be the same everywhere, and they have uniform density. Now, gas, on the other hand, is readily incompressible, so its density may vary quickly, while liquid and solid are not. Liquid and solid cannot be compressed readily. You have to apply a lot of pressure, a great pressure, to compress a fluid, to compress a liquid or solid. And the compression of a liquid and a solid is also very small compared with those of a gas. So for most of the situation, we ignore the change in volume of a liquid and solid. Okay. Now, what is pressure? Pressure is a unit, is a force acting on a unit area in a direction perpendicular to the area. That is the definition of pressure. Okay, so if you have a large area and you want to find the pressure at a certain position, now the pressure on different position in an area may be different. So if you want to find the pressure there at that particular position, you may like to look at the area, at a small area, which I call delta A. You look at the force, the normal force acting on that area, which I call delta F, and the force per unit area, delta F over delta A, is called the pressure. So the pressure is the force per unit area, but it only includes the normal force. Now, there may be tangential force, like, for example, friction. Friction is a tangential force, right? But friction is simply not accounted as pressure. We usually don't count the shear force as pressure. For a pressure force, we means the normal force. Usually, we means the normal force. Okay. Again, delta A is a macroscopically small area. So you can measure the pressure at different positions across a large surface. Okay. And if the pressure is uniform over a large area, then you simply skip the delta, and P become the total force divided by the total area. And of course, the unit for pressure is Newton per meter square. Newton is a unit for force, and meter square is the unit for area. So pressure has the unit of Newton per meter square, or we can term this unit as Pascal. Pascal, by definition, is Newton per meter square. Okay, and the standard atmospheric pressure is 1.01 times 10 to the power 5 Pascal. Now this number is not fixed. If you have a typhoon, then the pressure of air may drop substantially below this value. And if you have a high pressure area passing by Hong Kong, your pressure may go up. So you have a barometer that allows you to measure the pressure at different time. So the people in the Hong Kong observatory, they may have a broadcast to tell you what is the pressure today, what is the air pressure today. Okay. Now the important thing is that the force is, although the force is a vector, but pressure is a scalar. Okay, pressure is never defined as a vector. It's defined as a scalar. Okay, I will let you see why. The point is, if you are inside a fluid, the pressure force actually acts on all directions. For example, if you have a body immersed in water, you actually have pressure from different directions. Even if we are in air, we are exerted by atmospheric pressure on our body. The atmospheric pressure exerts a force on every part of my body. And for every part of my body, the force is exerted normally to the surface. For example, if my face is in kind of this way, the pressure exerted by atmospheric force, atmospheric pressure, is normal to my face. Okay, so that is the atmospheric pressure. That is the pressure force. Okay. Now, I will let you see. I will have a proof for you that the pressure force produced by the atmospheric pressure or the pressure for other fluids are the same in all directions. Now, imagine now, inside a fluid, we have a triangular volume. Suppose this is a right angle triangle for simplicity, and the angle is the right angle is here, and the angle alpha is this angle. So now we have this is a prism. Imagine we have a prism here inside the fluid. The prism is small, and so we have three areas. This area I call A1. The base area I call A2. At the hypotenuse of the triangle, we have another area where we call A3. The three areas are acted by the pressure P1, P2, and P3. We are now going to prove that P1, P2, and P3, they are all equal, as long as this triangle is small enough. It is small compared with the depth, for example, the depth of the below the fluid. Okay. Now, because the fluid inside the triangle is not moving, right? Okay, if you have an object inside the fluid and the object is not moving, so the force must get balanced. Okay, so now you have the x component of the force balance, and the x component of the force is what? The pressure produces a force in the x direction. The P1 pressure produces a force in the x direction. You have P1A1, and the force and the pressure P3 also produce a force in the x direction. The pressure force is P3A3, but you have to resolve that force in the x direction. So you have multiplied a sine alpha to find the x component of the force. Okay, and the x component of the force is negative, is direct in the negative x direction. So you put the negative sign here. And if the two forces are balancing each other, then the total force in the x direction is 0. Now, what happens if the two forces are not balancing? You will have this portion of fluid accelerating, but that's not observed, right? If you enclose a small volume of liquid inside a bulk of liquid, if the force is not balanced and the masses of this liquid is so small, this small volume of liquid must be accelerating, and the acceleration is infinite if the volume is so small. So that is not possible. So the obvious result is that the x component and the y component of the force are all balanced. Now, but we took a look at this formula. Now we can see that from this triangle, we can see that A1, this area, is A3 sine alpha. This is a simple relationship for a right angle triangle. A1 is A3 sine alpha. So actually, A1 and A3 sine alpha, they are equal, right? And so this equation will give me P1 equal to P3. So the pressure force, although they act on different direction, they are equal. Not the pressure force are equal, but the pressure are equal. Although they produce different pressure force of different direction. Okay. And also we can analyze the force balance in y direction. From the below, we have P2A2 as the pressure force, which is in the positive y direction. And we also have P3A3 cosine alpha as the pressure force on the hypotenuse side, which is downwards. Okay. And again, by trigonometry, we have A3 cosine alpha equal to A2. So the result is P2 equal to P3. And so all the pressure are equal. They are independent of the direction of action. Okay. Now, but the pressure force, the pressure produced by a fluid actually increase with the depth below the fluid surface. Okay. Suppose this is a fluid, the surface of a fluid. Suppose we have a water surface here, and we are somehow at the depth h below the water surface, and we want to find the pressure here. So how do we do that? We draw a cylinder, a long cylinder, with a small cross-sectional area, which I call A, and the height of the cylinder is of course h. And we study the force balance on this cylinder. The pressure force acting on this cylinder from the surrounding fluid is all in the horizontal direction because the force acts in the direction perpendicular to the surface. So that does not produce an upward force. The only upward force is produced by the pressure at the base of the cylinder. And suppose at the base of cylinder, the pressure is P, it produces upward force equal to PA. Does it make sense? Now, there is a pressure force due to what? Due to atmospheric pressure, but the atmospheric pressure force will cancel on both sides. So we can ignore it. The atmospheric pressure press on the cylinder at the top, but the force will also transmit it to the base. So the base will also contain the atmospheric pressure. So the two pressure will cancel. So we only consider fluid pressure. Okay. The fluid pressure is due to the pressure at the base of the cylinder and produce a force PA. But that will balance the weights of this water column. And the water column has a weight mg. Mg is given by the mass of the water column multiplied by the acceleration due to gravity. The cross-sectional area is A, the height is h. So AH is the volume multiplied by the density of water. Is the mass of water multiplied by G. So we can see the A cancel on both sides. And I get the pressure as rho GH. Okay. The pressure being proportional to the heights below the liquid column. Okay, because the surface of the liquid of the fluid. Okay. And also proportional to the density, of course. Now, but that may not be always true. We might have a situation in which the density may not be a constant. In case when we talk about gas, suppose we are talking about atmosphere, everybody knows that the density of the atmosphere decreases with altitude. If you go to a great height, the density will decrease. So the rho may be decreasing with height. Okay. How do we formulate that? how do we describe the change in density over a fluid that is compressible? We're going to do that. Now, the trick is to consider a small thin cylinder. The thickness of that cylinder is delta Ez, and we use an axis such that Ez pointing upwards is positive. So the cylinder has a thickness delta Z, and the gravity is pointing downwards, okay? Now the cylinder is being acted by two forces now. The pressure force from the base and the pressure force from the top. I claim that the pressure force from the base is slightly larger than the pressure force from the top, because the difference in the pressure force is used to maintain the balancing with the gravity. The gravity is pulling the metal downwards, so it's the weight of the cylinder. And the weight of the cylinder is actually balanced by the difference in pressure between the bottom and the top of the cylinder. Okay, so that is a story. That is how the cylinder, the mass, the weight of the cylinder is balanced. It's balanced by a difference in pressure. Now we do the calculation. At the base of the cylinder, the pressure is Pz. We call this level Ez. So the pressure force is Pz multiplied by A. At the top of the cylinder, the height is Ez plus delta Z. The pressure at the top is Pez plus delta Z. Again, we multiply by A, we get the pressure force, but the pressure force is downward, so we have a minus sign. We take the upward direction as positive, so the first term upward is positive. The second term downward is negative. And the difference in the pressure, the two forces, will just balance the weights of the cylinder, which is delta mg. And delta m is the volume of the cylinder, which is A delta Z. The base area multiplied by the height is the volume, multiplied by the density of the fluid. And that means the mass of the cylinder. Now, if I divide this equation by delta Z, I will get the following. I put the minus sign on the right-hand side. I have Pez plus delta Z minus Pz divided by delta Z being equal to minus rho g. I realize that this combination, when delta Z tends to 0, is exactly dP dZ. It is a definition of the derivative, right? P evaluated at Ez plus delta Z minus P evaluated Ez divided by delta Z is just the derivative of P with respect to Ez. So that means dP dZ is equal to minus rho g. Okay. Now that what does that mean? That means the pressure is decreasing with heights. Ez is going up. So when I go up, the change in pressure is negative. The rate of change of pressure is negative. That means when I go up, the pressure is decreasing. Okay, that is what you observe. When you go to a high altitude, the pressure decreases. And if you want to integrate this equation, if you want to find the dependence on P with Cz, you have to know the density variation. So if you assume a certain model of the density of air with heights, you can integrate this equation to obtain the pressure, the change in pressure with heights. That is what we are going to do in the next lecture. We better stop here. We have long lecture already. So we stop here today, and